Microsoft Fabric Data Warehouse Deep Dive, the complete guide to OneLake, SQL security, performance, and migration. Hello and welcome. In this deep dive, we will explore Microsoft Fabric Data Warehouse as a modern enterprise analytics platform rather than simply another cloud-based SQL database. Fabric Data Warehouse is designed for large-scale relational analytics workloads, but it is built on a lake-centric architecture that uses OneLake and Delta tables as the storage foundation. This unified approach allows SQL developers, data engineers, BI professionals, governance teams, and business analysts to work with the same trusted data without unnecessary duplication across multiple systems. The platform combines data warehousing, integration, security, governance, and reporting within a shared software as a service environment. By the end of this discussion, you will understand how Fabric Data Warehouse works, where it fits in modern architectures, how to secure and monitor it, and how organizations can plan successful real-world adoption strategies. The challenge Microsoft Fabric Data Warehouse addresses is common across many enterprise data environments. Organizations often operate separate platforms for data lakes, enterprise warehouses, ETL pipelines, semantic models, governance controls, monitoring systems, and reporting tools. Over time, this creates duplicated data, inconsistent security policies, disconnected operational processes, and too many handoffs between engineering, analytics, and business teams. Microsoft Fabric attempts to unify these capabilities within a single SaaS-based analytics ecosystem where data can be ingested, transformed, modeled, queried, secured, governed, and reported from a shared platform. Within this architecture, the warehouse workload becomes the SQL first serving and modeling layer that supports governed enterprise analytics while remaining tightly integrated with the broader Fabric ecosystem. Microsoft Fabric Data Warehouse is best understood as an enterprise relational warehouse built on top of an open data lake architecture. It is designed primarily for structured analytical workloads such as dimensional models, star schemas, snowflake schemas, curated enterprise data marts, semantic modeling, and large-scale business intelligence reporting. Data is stored using Delta tables built on Parquet files and transaction logs, providing both open storage flexibility and transactional consistency. This architecture allows Fabric to support familiar warehouse capabilities while still benefiting from modern lake-based interoperability and scalability. Developers primarily interact with the warehouse through T-SQL, while tools such as Power BI, SQL clients, notebooks, and external applications can consume the data through Fabric SQL endpoints and standard connectivity mechanisms. Microsoft Fabric provides two related SQL experiences that serve different purposes and should not be confused during architecture planning. A warehouse item provides the full SQL warehouse experience, supporting many DDL and DML operations, stored procedures, functions, materialized views, transactional operations, and enterprise warehouse development workflows. In contrast, a SQL Analytics endpoint is automatically generated for Lakehouse and certain other Fabric items to expose Delta tables through a SQL query interface. The SQL Analytics endpoint is highly useful for querying lake-based data, building views, defining security, and supporting reporting scenarios over Delta storage. However, it does not provide the same full read-write warehouse functionality or transactional warehouse development experience available within a dedicated warehouse item. Selecting the correct approach depends on whether the requirement is full warehouse development or SQL-based access to Lakehouse managed data. The warehouse and Lakehouse experiences in Microsoft Fabric are designed to complement each other rather than compete directly. Organizations should generally use Fabric Data Warehouse when workloads are primarily SQL-driven, data is highly structured, and the objective involves governed enterprise BI, dimensional modeling, curated reporting layers, and relational analytics. Lakehouse environments are more appropriate for Spark-based processing, notebooks, raw and semi-structured data handling, machine learning workflows, unstructured file processing, and medallion-style engineering architectures. In many enterprise implementations, the Lakehouse manages bronze and silver engineering layers, while the warehouse provides curated gold layer business models optimized for reporting and semantic consumption. Fabric makes this integration practical because both warehouse and Lakehouse workloads operate on OneLake and share open Delta-based storage foundations. OneLake is a foundational component of the Microsoft Fabric architecture and plays a central role in how Fabric Data Warehouse operates. Instead of treating the warehouse as an isolated storage system with tightly coupled compute and proprietary data layers. Fabric stores warehouse data in OneLake using open Delta table formats built on Parquet files. This architecture allows multiple Fabric workloads and engines to access shared data through governed and secure access paths without unnecessary duplication. SQL developers, Spark engineers, Power BI modelers, data scientists, and administrators can all work with the same underlying data state while using different tools and processing engines. This shared lake-centric design is one of the major differences between Fabric Data Warehouse and older warehouse-only platforms that relied heavily on isolated storage and duplicated analytical datasets. The high-level architecture of Microsoft Fabric Data Warehouse includes several integrated components that work together to deliver scalable, distributed analytical processing. A unified query optimizer evaluates incoming SQL queries and determines efficient execution strategies based on workload characteristics and data distribution. A distributed query processing layer then divides execution plans into parallel tasks that can run across back-end compute resources within the Fabric environment. The query execution engine processes Delta Parquet data stored in OneLake using techniques such as distributed execution, columnar processing, caching, and batch operations optimized for analytics workloads. Metadata and transaction management services maintain schema consistency, table versions, transaction state, and reliable ACID-compliant operations across the platform. Together, these architectural layers allow Fabric Data Warehouse to support enterprise-scale analytical workloads while remaining integrated with the broader OneLake ecosystem. The Query Optimizer in Microsoft Fabric Data Warehouse is designed to reduce the need for extensive manual query tuning and infrastructure-level optimization. When a SQL query is submitted, the optimizer evaluates possible join strategies, data movement patterns, table statistics, resource utilization, and data distribution characteristics to determine an efficient execution plan. It can decide whether smaller data sets should be broadcast across compute nodes, whether large data sets should be shuffled between distributed execution resources, or whether joins should be reordered to reduce execution cost. These optimization decisions are especially important because enterprise warehouse environments often contain highly complex SQL workloads created by developers and analysts with varying levels of experience. Fabric attempts to automate many optimization activities traditionally managed manually by database administrators in older analytical systems. This approach helps simplify warehouse operations while still supporting scalable analytical performance. The distributed query processing architecture provides Microsoft Fabric Data Warehouse with elastic scalability for analytical workloads. Queries are divided into smaller execution tasks that can run in parallel across multiple back-end compute resources within the Fabric platform. Fabric also separates select-based analytical workloads from non-select activities such as ingestion, transformation, and loading operations to reduce contention between reporting and engineering processes. This workload isolation is particularly important in enterprise environments where dashboards, ad hoc analytics, scheduled transformations, ingestion pipelines, and operational reporting may all execute concurrently. Backend compute resources can scale dynamically depending on workload demand, concurrency patterns, and available Fabric capacity. This distributed execution model allows the warehouse to support large-scale analytical processing without relying on traditional fixed infrastructure scaling approaches. The query execution engine in Microsoft Fabric Data Warehouse processes analytical data directly from Delta Parquet files stored within OneLake. To improve performance and reduce repeated remote storage access, the engine uses memory-based and SSD-based caching mechanisms for recurring workloads and frequently accessed datasets. It also applies optimization techniques such as column elimination and row group elimination so that queries scan only the necessary portions of data when selective filters and projections are applied. Batch mode execution enables the engine to process large sets of rows efficiently in analytical scenarios instead of handling records individually in row-by-row execution patterns. These capabilities are particularly valuable for large-scale aggregations, filtering operations, joins, business intelligence reporting, and high-volume analytical workloads where efficient distributed execution is critical for performance and scalability. Metadata and transaction management are essential because Fabric Data Warehouse operates on open lake-based storage rather than a traditional isolated database engine. The platform maintains awareness of table schemas, physical data files, transaction states, committed changes, and version history to ensure consistent query results and reliable operations. Fabric extends actual style transactional behavior over Delta-based storage so users can work with trusted and consistent table states across concurrent workloads. These capabilities also support advanced features such as time travel, cloning, recovery scenarios, and point-in-time data operations. Data ingestion in Microsoft Fabric Data Warehouse can occur through multiple integration and loading methods depending on workload requirements. Teams can use Fabric pipelines, data flows Gen 2, copy jobs, copy into commands, CTOS operations, insert select statements, select into operations, cross-database ingestion, and Spark-based writes into Delta tables stored in OneLake. These ingestion paths support both low-code and code-first development approaches, allowing organizations to integrate data from operational databases, SaaS applications, files, APIs, streaming systems, and external data lakes. The appropriate congestion strategy depends on data volume, transformation complexity, latency expectations, governance requirements, and operational preferences. Organizations should also consider monitoring, retry handling, orchestration, and data quality validation as part of enterprise ingestion design. Mirroring is an important near real-time data integration capability within Microsoft Fabric. It enables supported external systems to continuously replicate data into OneLake with reduced dependency on custom extraction and replication pipelines. Fabric documentation describes mirroring support for sources, including Azure SQL Database, Azure SQL Managed Instance, Azure Cosmos DB, SQL Server, Snowflake, PostgreSQL, Databricks, and open mirroring scenarios for additional platforms. Mirroring is particularly useful when analytics teams need operational data synchronized into Fabric for reporting, analytics, and downstream warehouse modeling. Organizations should carefully evaluate source system impact, replication latency, security boundaries, governance controls, network considerations, and consistency requirements before implementing large-scale mirroring architectures. Microsoft Fabric Data Warehouse supports standard enterprise data warehouse modeling practices commonly used in analytical systems. Fact tables are typically designed to store measurable business events such as sales transactions, financial activity, inventory movements, shipments, telemetry, or user interactions. Dimension tables provide descriptive business context such as customer, product, employee, geography, account, supplier, or calendar attributes that support filtering and analytical reporting. Integration and staging tables can be used to cleanse, standardize, and transform incoming data before loading curated dimensional models. This modeling approach aligns well with Power BI semantic models because dimensional structures are generally easier to understand, govern, optimize, and secure for enterprise reporting and self-service analytics. Table and schema design in Fabric Data Warehouse requires awareness of platform-specific architectural considerations. The warehouse supports many familiar T-SQL data types, but not every SQL Server data type is supported for persistent storage within the distributed warehouse engine. Unsupported or limited types may include XML, geography, geometry, tinyInt, money, image, text, end-text, SQL tokens, name, underscore variant, and certain legacy SQL Server specific types. JSON is supported through string-based storage and SQL functions rather than as a native persistent JSON data type. In many scenarios, architects should use alternatives such as varchar, decimal, var-binary, badging, or modeled relational structures. Warehouse collation is defined during warehouse creation and cannot currently be modified afterward, so collation planning should be completed carefully before migration or large-scale production deployment. Constraints in Microsoft Fabric Data Warehouse behave differently from those in traditional transactional relational database systems. Primary key, unique, and foreign key constraints are currently supported only as informational metadata and are not enforced by the distributed warehouse engine. Primary key and unique constraints are implemented as non-clustered and not enforced, while foreign keys are also supported only as not enforced relationships. These constraints can still help developers, BI tools, semantic models, and query optimization processes understand table relationships and intended data structures. However, data quality Referential integrity, duplicate prevention, and validation logic must be handled through ETL processes, transformation pipelines, testing frameworks, governance controls, and operational monitoring rather than relying on the warehouse engine to enforce relational consistency automatically. Identity columns are commonly used for surrogate keys in dimensional models, but their behavior in Fabric reflects the realities of distributed processing systems. Microsoft Fabric Data Warehouse supports identity only on Bayesian columns, and identity values are generated and managed automatically by the platform. The generated values are unique and positive, but are not guaranteed to be sequential, gap-free, or ordered because values may be allocated across multiple distributed execution tasks simultaneously. Features commonly associated with traditional SQL Server identity behavior, such as reseeding, custom increment values, and identity insert operations, are limited or unsupported in Fabric Warehouse scenarios. This behavior is generally acceptable for surrogate keys and analytical systems, but migration teams should carefully review assumptions built into legacy ETL processes, reporting logic, and application dependencies. T-SQL remains the primary development language for Microsoft Fabric Data Warehouse, allowing SQL professionals to work with familiar query and schema management patterns. Supported functionality includes commands such as create table, ctos, insert select, select into, views, store procedures, functions, and a wide range of analytical query operations. However, Fabric is architecturally different from traditional SQL Server because it is built as a distributed, lake-centric analytical warehouse rather than a single-node relational engine. As a result, some SQL Server capabilities, syntax patterns, transaction behaviors, temporary object scenarios, and administrative operations may behave differently or may not be fully supported. Development teams should validate scripts, data types, constraints, object dependencies, and migration assumptions early in the implementation lifecycle to reduce production migration risk and compatibility issues. Querying and development in Microsoft Fabric Data Warehouse can be performed through multiple integrated and external tools. Users can access warehouse data using the Fabric SQL Query Editor, Visual Query Editor, notebooks, Power BI, SQL Server Management Studio, Visual Studio Code, ODBC, OLTB, JDBC, DBT, and custom client applications. Both warehouse items and SQL Analytics endpoints expose a TDS endpoint, allowing connectivity through many SQL-compatible tools and drivers. Authentication is based on Microsoft Entra ID, providing centralized identity and access management across Fabric services. When establishing external connections, users should specify the warehouse or database name as the initial catalog parameter because the endpoint alone is insufficient for reliable database context resolution and connection management. Cross-database querying is one of the most valuable analytical capabilities in Microsoft Fabric Data Warehouse. Queries can reference tables and views across warehouses, SQL Analytics endpoints, Lakehouse objects, and other supported Fabric items within the same workspace using familiar three-part naming conventions. This enables zero-copy analytics patterns where data can remain in separate storage and processing domains while still being joined together for reporting, transformation, and analytical workloads. For example, a curated warehouse fact table can be joined with a Lakehouse dimension or mirrored operational dataset exposed through a SQL Analytics endpoint. This approach reduces unnecessary data duplication, improves architectural flexibility, and allows SQL developers to work with distributed analytical assets using familiar relational query patterns. Microsoft Fabric supports querying external and open data formats using SQL-based access patterns across OneLake and supported storage locations. Users can work with delimited text files, CSV files, JSON files, Parquet files, and Delta tables depending on the supported scenario and query method. This capability allows developers and data engineers to inspect raw external data, validate incoming datasets, build staging and transformation flows, and integrate open Lakehouse data into analytical processes. External querying is useful for exploration and flexible integration, especially during ingestion and engineering workflows. Enterprise reporting and governed analytics should generally rely on curated warehouse or Lakehouse tables that provide managed schemas, security controls, optimized statistics, consistent governance, and more predictable query performance. Time travel and table cloning are important capabilities in Microsoft Fabric Data Warehouse for recovery, testing, development, and operational resilience. Time travel allows users to query table data as it existed at an earlier point within the configured retention window, making it possible to investigate historical states, recover from logical issues, or validate changes over time. Table cloning enables rapid creation of table copies without immediately duplicating all underlying physical storage, helping accelerate development, testing, sandboxing, and robot-style workflows. Clones can be created using either the current state of a table or a previous point-in-time version. After creation, clone tables operate independently, meaning future changes to the source table do not automatically affect the clone and vice versa. Warehouse snapshots provide another mechanism for working with stable point-in-time analytical states within Microsoft Fabric environments. Snapshots can help support reporting consistency, validation processes, audit scenarios, and operational recovery workflows by preserving a view of warehouse data at a specific moment. In enterprise analytics environments, snapshots are especially valuable when business users require stable reporting outputs while ingestion pipelines and transformation processes continue updating the underlying warehouse tables. Snapshots can also support deployment validation, testing, historical comparisons, and controlled release processes during warehouse lifecycle management. Organizations should still plan snapshot usage carefully by considering storage consumption, retention policies, governance requirements, security boundaries, and operational maintenance practices. Security in Microsoft Fabric Data Warehouse operates across multiple integrated layers of the Fabric platform and SQL engine. Access control combines Microsoft Fabric workspace permissions, item-level permissions, workspace roles, and SQL granular security to provide flexible governance across analytical workloads. At the Fabric platform layer, users typically require at least read permission to access and connect to warehouse resources. Workspace roles such as admin, member, contributor, and viewer apply broadly across items contained within a workspace, while item-level permissions can provide more targeted access to individual warehouse assets. Security then adds finer-grained controls for schemas, tables, views, procedures, rows, and columns within the warehouse environment. The principle of least privilege is a critical best practice when designing security for Microsoft Fabric data warehouse environments. Elevated workspace roles such as admin, member, and contributor should generally be limited to users actively developing, administering, or managing the analytical solution because these roles can affect many resources across the workspace. Users who only require reporting or read-only analytical access should typically receive limited item permissions together with targeted decode-level access to approved schemas, views, or tables. Microsoft Entra Groups can simplify enterprise-scale access management by allowing permissions to be assigned to organizational groups instead of individual users. Applying least privilege design principles helps reduce security risk, simplify governance, and prevent permissions from becoming excessively broad as Fabric adoption expands across the organization. Sync-while granular permissions in Microsoft Fabric Data Warehouse use familiar relational database security concepts to control access at multiple levels. The platform supports grant, revoke, and deny operations for managing object-level access permissions, along with support for database roles and custom permission assignment strategies. Object-level security can restrict access to tables, views, stored procedures, functions, and other warehouse objects based on user responsibilities. Role-level security allows organizations to filter records dynamically so users can view only authorized subsets of data based on security predicates and identity context. Column-level security and dynamic data masking help protect sensitive information such as personal identifiers, financial records, healthcare data, and confidential business attributes while still supporting broader analytical access where appropriate. SQL audit logging helps organizations monitor and track warehouse activity for governance, compliance, operational monitoring, and security investigations. Microsoft Fabric Data Warehouse can capture events such as authentication attempts, query execution, data access, schema modifications, permission changes, administrative actions, and other security-related activities. Audit logs are stored in OneLake in XCL file format within the warehouse audit logging location and are encrypted at rest as part of the platform's security model. Auditing is not automatically enabled by default, so authorized administrators must configure and enable the required audit settings. Organizations should carefully select the events they choose to capture because extensive audit logging can increase storage usage, monitoring complexity, and operational overhead in large-scale analytical environments. Encryption is an important part of the overall Microsoft Fabric data warehouse security architecture. By default, Fabric uses Microsoft managed encryption mechanisms to protect data stored within the platform, including warehouse and OneLake storage layers. For organizations with stricter regulatory or compliance requirements, customer managed keys can be configured in supported environments to provide greater administrative control over encryption management. When customer managed keys are enabled, both warehouse metadata and OneLake data can be protected using encryption keys stored and managed through Azure Key Vault. This capability is particularly important for regulated industries and enterprises that require centralized key lifecycle management, rotation policies, and stronger control over sensitive analytical assets. Effective security architecture should combine encryption with identity management, permissions, auditing, masking, role-level security, and governance controls rather than relying on encryption alone. Power BI integration is one of the most important advantages of Microsoft Fabric Data Warehouse because it connects governed warehouse data directly to enterprise reporting and analytical experiences. Warehouse data can be used to build semantic models, interactive Power BI reports, dashboards, and other analytical experiences within the Fabric ecosystem. Well-designed dimensional models remain important because semantic models built on clear fact and dimension structures are generally easier to optimize, govern, secure, and understand for business users. Fabric documentation also highlights evolving behavior around automatically generated semantic models, so organizations should explicitly design, manage, and govern semantic models rather than depending entirely on default automation. Strong semantic modeling practices remain essential for delivering trusted, scalable, and business-friendly enterprise analytics solutions. Microsoft Fabric supports both professional developer workflows and self-service analytical experiences across different user groups. SQL developers and data engineers can work with SQL query editors, T-SQL notebooks, a SQL Server Management Studio, Visual Studio Code, warehouse projects, source control integration, and DBT-style development patterns. Business analysts and citizen developers can use visual query experiences, Power BI semantic models, dashboards, and reporting tools to consume and analyze warehouse data. Data engineering teams can integrate pipelines, data flows Gen 2, notebooks, shortcuts, and Lakehouse-based processing into broader enterprise workflows. While this flexibility improves collaboration and productivity across teams, organizations must still establish governance standards to prevent business critical logic, transformations, and security rules from becoming fragmented across too many disconnected tools and development practices. Copilot capabilities in Microsoft Fabric Data Warehouse can improve SQL productivity and accelerate development workflows, but they should be used with careful review and governance. Copilot can generate T-SQL queries from natural language prompts, explain existing SQL statements, provide code completion suggestions, summarize logic, and assist with troubleshooting and error correction. The system uses metadata such as table names, column names, relationships, primary keys, and foreign key definitions to help generate context-aware SQL recommendations. However, Copilot does not use the actual underlying table data to generate query suggestions, helping reduce direct exposure of business data during assistance workflows. Users should still validate generated SQL carefully because AI-generated outputs may contain incorrect assumptions, inefficient logic, unsupported syntax, or incomplete business rules. Clear naming conventions, accurate schema design, well-defined relationships, and precise prompting practices can significantly improve Copilot effectiveness and reliability. Performance optimization in Microsoft Fabric Data Warehouse is partially automated, but effective warehouse design and query tuning remain important responsibilities for engineering teams. The platform automatically manages many distributed execution decisions, such as task scheduling, parallel execution, and data movement strategies, reducing the need for extensive manual infrastructure tuning. However, strong performance still depends on good schema design, properly aligned join data types, selective filtering, efficient query logic, and well-structured dimensional models. Statistics play an important role by helping the query optimizer estimate row counts, execution cost, and data distribution patterns when generating execution plans. Fabric can automatically maintain statistics in many scenarios, and developers can also create or update supported statistics objects during planned maintenance windows. Poorly designed schemas, unnecessary type conversions, excessive scans, inefficient joins, and oversized tables can still significantly reduce query performance in analytical workloads. Caching mechanisms help improve the performance and consistency of repeated analytical workloads within Microsoft Fabric Data Warehouse. The platform uses memory-based and SSD-based caching to reduce repeated remote storage access against OneLake and improve execution efficiency for frequently accessed data. Query execution can also benefit from column elimination, row group elimination, and optimized distributed execution paths that reduce unnecessary data scanning. Result set caching is described in Fabric documentation as a performance optimization capable of reusing previously generated select query results for repeated workloads such as dashboards and recurring analytical reports. However, current documentation also notes that result set caching is temporarily disabled in Fabric Data Warehouse because of a known issue. Organizations should therefore avoid designing production performance strategies that depend entirely on result set caching behavior until the capability is fully supported and operationally stable. Monitoring and observability are essential for operating Microsoft Fabric Data Warehouse effectively in enterprise environments. Fabric provides tools such as query activity, which displays running and historical SQL query execution details, and query insights, which helps analyze completed, failed, canceled, long-running, and frequently executed queries. Dynamic management views, commonly referred to as DMVs, provide additional operational visibility into sessions, requests, connections, execution state, and workload behavior. The Microsoft Fabric Capacity Metrics application helps administrators monitor compute usage, capacity consumption, throttling conditions, and workload pressure across Fabric resources. Together, these monitoring capabilities help engineering teams identify expensive queries, failed ingestion jobs, concurrency bottlenecks, inefficient workloads, and capacity saturation issues. Effective monitoring should be treated as an ongoing operational discipline rather than only a troubleshooting activity during incidents. Capacity management in Microsoft Fabric differs significantly from managing traditional dedicated database servers or manually provisioned infrastructure. Fabric uses a capacity-based compute model that includes concepts such as workload smoothing, throttling, burstable resource consumption, pause and resume behaviors, and dynamic workload management across shared services. When a Fabric capacity becomes overloaded, certain warehouse operations may be delayed, throttled, or rejected depending on workload priority and current resource conditions. During severe capacity pressure scenarios, some dynamic management views and operational diagnostics may become less available, requiring administrators to rely more heavily on the Fabric Capacity Metrics application for troubleshooting and root cause analysis. Successful operations therefore require proactive workload planning, careful monitoring of compute consumption, scheduling of large transformation jobs, and continuous review of workload distribution patterns across the environment. Workload management is deeply integrated into the architecture of Microsoft Fabric Data Warehouse and plays a critical role in maintaining scalable analytical performance. The SQL front end first parses and optimizes submitted queries before the distributed query processing engine divides the execution plan into smaller parallel tasks that run across backend compute resources. Fabric can dynamically allocate additional backend resources and provision new compute capacity quickly when workload demand increases and capacity is available. The platform is designed to support concurrent analytical, ingestion, and transformation workloads without requiring extensive manual infrastructure management. However, organizations should not assume that compute resources are unlimited or that all workloads will automatically perform efficiently without optimization. Teams should continue to separate heavy workloads where appropriate, optimize recurring queries, minimize unnecessary scans, monitor user-generated and system-generated activity, and implement governance practices that prevent uncontrolled resource consumption across shared analytical environments. Development and deployment for Microsoft Fabric Data Warehouse should be treated as disciplined software engineering work rather than manual database editing. Fabric supports warehouse projects in Visual Studio Code and source control scenarios, helping teams manage warehouse artifacts more systematically across development, test, and production environments. This matters because warehouse solutions include schemas, tables, views, stored procedures, functions, permissions, security definitions, deployment scripts, and environment-specific configuration. Mature teams should version control these assets, review changes, test deployments, and promote validated objects through controlled release processes. A production warehouse should not become a collection of manually edited scripts that only exist in the portal or in individual developer workspaces. Strong lifecycle management improves reliability, auditability, collaboration, and long-term maintainability. Data recovery planning in Microsoft Fabric Data Warehouse should combine multiple platform capabilities rather than depend on a single rollback method. Recovery options can include restore in place, table cloning, time travel queries, warehouse snapshots, and carefully governed backup or validation processes depending on the scenario. These features reduce operational risk when ingestion jobs, transformation logic, schema changes, or deployments introduce incorrect data or unexpected behavior. They are especially useful during development, migration testing, release validation, and incident investigation because teams can compare current and prior states of data. Recovery design should account for retention windows, permissions, business impact, audit requirements, and recovery time expectations. The key lesson is that recovery should be planned, tested, and documented before a production failure occurs. Migration to Microsoft Fabric Data Warehouse requires careful planning, especially for organizations moving from Azure Synapse Analytics, dedicated SQL pools, SQL Server, or other SQL database engine-based platforms. The Fabric Migration Assistant can support assessment, schema conversion, data copy, and connection rerouting activities, but it does not eliminate the need for architectural validation. Teams must review supported data types, identity column behavior, unsupported objects, constraint semantics, stored procedures, security models, indexes, workload patterns, reporting dependencies, and downstream ETL logic. Migration should not be treated as a simple lift and shift of tables because Fabric is a distributed, lake-centric analytical platform with different storage, execution, and governance characteristics. Successful migration usually requires testing, parallel validation, performance comparison, security review, and phase cutover planning before production reports and data pipelines are redirected. The best Microsoft Fabric data warehouse architecture is usually built iteratively around clear business priorities rather than as a single large migration project. Teams should begin with high-value subject areas, design strong fact and dimension models, define security requirements early, create semantic models intentionally, monitor workload behavior, and expand the platform over time. Lakehouse should be used for raw files, semi-structured data, Spark processing, notebooks, and engineering-heavy workflows, while Warehouse should be used for SQL-first curated analytics, governed dimensional models, and enterprise reporting layers. Mirroring can support operational data replication into Fabric, and Power BI can provide the business consumption layer through semantic models and reports. Data duplication should be avoided unless there is a clear reason related to performance, transformation, governance, or resilience. Fabric Data Warehouse delivers the most value when it operates as part of a unified analytics architecture rather than as another isolated database.
The final takeaway is that Microsoft Fabric Data Warehouse is a SQL-first analytical warehouse designed for the OneLake era. It combines Open Delta storage, distributed query processing, T-SQL development, Power BI integration, security controls, monitoring capabilities, recovery features, lifecycle tooling, and AI-assisted development into a unified Fabric experience. It is not identical to SQL Server or Azure Synapse Analytics' dedicated SQL pools, so teams must understand its distributed architecture, supported feature set, security model, capacity behavior, and platform-specific limitations. When designed carefully, it can simplify modern analytics architecture by reducing data duplication, improving governance, and connecting SQL Lakehouse engineering and BI workflows. For organizations building future-ready analytics platforms, Fabric Data Warehouse offers a practical path toward governed, scalable, and business-friendly data solutions.
Thank you for taking the time to explore this topic. See you in the next video.